So I would like to start by saying that I am not an expert in this area. This is something I've learned for about a semester as part of a reading project. So I'm not an expert, but I still know enough to find it quite interesting and to share it with you. It's reverse mathematics is an area with a very interesting big picture, but unfortunately for purposes of explaining it to people, it's also a very technical area in the sense that you really do need a lot of technical details to understand, exactly why things are true and to justify precisely. So I'm sorry to say that proofs are going to be a lot very, I'm not actually going to be proving anything. I'm going to be explaining how you might prove it if you knew all the details. But regardless, the interesting part of reverse mathematics is not the technicalities, it's the big picture, and I hope to give you a good overview of the big picture. I'm going to put in my setup. So reverse math. Are you able to read clearly? Do I need to write bigger? Is this? Give me some feedback. I can't see any cameras other than the classroom. So if people are giving, okay, great. Someone said great in chat. That's terrific. Okay. So the first thing I want to do is I want to talk about something that's not reverse math, or it's sort of like proto-reverse math. It's a funny anecdote. And it goes back to the 1920s. I really like this anecdote, so some of you maybe have already heard it, but I will say it anyway. So it all starts when Tarski proves a theorem. And the theorem he proves is that under ZF, the axiom of choice is equivalent to the statement that for any infinite set A is in bijection with a Cartesian product A. For us these days, this is a standard type of theorem. We're all used to, oh yeah, the axiom of choice is equivalent to this and that and that. But at the time, it was quite revolutionary. And so he took this up, he wrote it into a paper, and he tried to publish it into this journal called Comptes Rendus. And he got rejected. And the reason why he got rejected is very interesting, because there were two very famous people, we still know them these days, called Fréchet and Lebesgue, who were the people who were responsible for rejecting him. And here are the reasons they gave for the rejection. So Fréchet said, oh, you just proved that something true is equivalent to something true, and that's not new. While Lebesgue said, oh, proving that something false is equivalent to something false is uninteresting. So, obviously, given these two contradictory feedbacks, Tarski was very upset. He swore never to publish in this magazine. What's the word? Anyway, he swore never to publish here again, and yeah, he went and published this somewhere else. Now, the reason why I'm giving you this story is because it is it represents some changes, some interesting changes of perspective that happened in mathematics in the last century. So the first one, so paradigm changes. The first one is that now we see the axiom of choice as not either true or false, but rather as something we can choose to accept or not. And that this depends on the, on how we're feeling at the moment, right? I mean, I can do a proof and use the axiom of choice and say I use the axiom of choice here, but maybe in some other thing that I'm doing, I'm interested in what happens if I don't have the axiom of choice, and so I just don't accept the axiom of choice. And for us, that's perfectly natural, but clearly back at the time, even for very advanced mathematicians, this was a very strange concept, because a lot of people still had this idea of mathematics as absolute truth. The second paradigm shift that I want to say, which is kind of related, is that at the time, let's stick with Fréché's perspective, because it's the one that's, if in any of these two is more common in mathematics these days, it's Fréché's, which is accepting the axiom of choice. Fréché said, oh, you prove that two true things are equivalent, and that's not interesting. But the second paradigm change that I want to say is that proving an equivalence between true things can be interesting. And in fact, that's the whole point of reverse mathematics. We're going to take statements which are true in ordinary mathematics, and we're going to prove that they're equivalent, and that's going to be interesting. And this is a good microcosm of how we can do that and why that's interesting. So the idea is that since we are working with ZF without the axiom of choice, these two statements are not true nor false. And so proving an equivalence between them is really something interesting. You're really doing something new that isn't already present there, if that makes sense. And I mean, even if you're not like under this very formal point of view, we already know that this can be interesting, because a lot of like, I don't know, I remember when I learned calculus, one of the exercises was to prove that the inverse function theorem was equivalent to the implicit function theorem or something. And, if I was Fréché, I would have just said they're both true, they're equivalent, of course. But no, that's not the point. The point is to show that there's like a very direct connection between them. Okay. All right. So without losing much more time, let's just figure out how we can make this interesting. How did Tarski make this statement interesting? What he did was he work in a weaker set of axioms where T1 and T2 are not necessarily true. And so proving an equivalence does become something interesting. And you can do this with ZF. Again, this is one of the first examples, but there's a problem, which is that ZF or ZFC is very fragile. Because, I mean, if you look at the axioms of ZFC and you think about, okay, what axioms can I remove? Okay, you can remove the axiom of choice. That still gives you a lot of interesting math. You can remove the axiom of foundation, because no one but set theorists care about it. But it's still not going to give you anything very interesting, because also there's no standard mathematical facts that require the axiom of foundation. You can remove the axiom schema of substitution to get what's called Zermelo set theory, which is Z, which is a strict subset of ZF. And this could also be interesting, but you can still do a lot of ordinary mathematics here. So you could, you still don't get any, you're not going to be able to prove that, I don't know, the mean value theorem is equivalent to something else or something like that. And if you remove more, you get garbage. This is supposed to be a trash can. Because as it turns out, if you take this thing and you try to remove anything, I mean, probably there's a lot of things you can remove, but they're not going to be natural. If you try to remove anything in a natural way, you're going to get some piece of garbage set theory that doesn't prove anything. Like, it doesn't prove that the natural numbers exist or the real numbers exist or something. So ZFC is not a good place to try to do these things. Are there any questions so far? Okay. So let me introduce you to the replacement of ZF or ZFC, which is second order arithmetic. As a side note, if you want to learn reverse mathematics, you probably are going to look up books called Reverse Mathematics. But as it turns out, one of the biggest books, and the one I learned this from, is a book by Simpson, which is called Subsystems of Second Order Arithmetic, which was very confusing to me when I started out, because I was like, okay, but I want to learn reverse math, not second order arithmetic. But as it turns out, at least in the lower levels, they are basically the same thing. Okay, so what is second order arithmetic? So we all know that ZFC is trying to describe the universe of sets and set inclusion. Second order arithmetic, which I'm going to call Z under 2, describes the universe of the natural numbers and the subsets of natural numbers. And so, in ZFC, you only have basically the symbol and you have variables that represent sets. Here, we're going to have a lot more structure. So we're going to have, first of all, we're going to have two types of variables. So we have lowercase letters, which represent natural numbers, and we have uppercase letters, which represent sets of natural numbers. We can ask whether an element is in a set. And then between natural numbers, we have plus, times, 0, 1, less than, all of them. Yes. So this is the language of second order arithmetic. And the axioms, I'm not going to write them all out in the same way that I wouldn't write all the axioms of ZFC out, but I'm going to roughly tell you what they are. And I like to divide them into 3 categories of axioms. So actually, I'm going to do this here because, okay. I'm going to try something a little weird to save myself some time in the future. So here are the axioms of Z2. So first we have some things that I'm going to call arithmetic axioms, which are just things that are true of the natural numbers and are very obvious, and of course we won't have them as axioms. For example, for every number, it is not the case that that number plus 1 equals 0. Or for every 2 numbers, if n plus 1 equals m plus 1, then n equals m. Or addition and multiplication are commutative and associative. And there's a bunch of axioms like this, and I don't want to write them all out, but you can imagine roughly what they would be. Then we have comprehension, which is what's going to let us build sets. So morally, this is saying that we can write something like this. And so it's something of the form for every formula phi with some free variables, we add an axiom saying that there exists a set such that a number is in the set if and only if it satisfies the formula. And for every formula, we add an axiom like this. And finally, we have induction. Of course, we couldn't have the natural numbers without induction. And again, for formulas phi of x, we add an axiom saying that if phi is true at 0 and for every x, phi at x implies phi at x plus 1, then for all x, phi of x. And okay, there's some technicalities here that I'm not mentioning, namely these formulas can have parameters, but this enters into the realm of technicalities. If I get into, I will spend a lot of time, and the people who already know aren't going to learn anything, and the people who don't know aren't going to learn anything either because I'm going too fast. So I'm going to introduce some notation, which is this danger sign, which means that I'm sweeping something under the rug and probably lying. But morally true. And so when you see this, that means that, and I'm applying it to here. But anyway, roughly speaking, this is the axioms of second order arithmetic. They're more or less what you'd expect if you were trying to describe the natural numbers. And this system was introduced by Hilbert and Bernet in 1934, but it was Harvey Friedman who in 1974 thought to apply this to reverse mathematics. So this was the guy who thought that this was a set of axioms that could replace ZFC and that we could remove stuff from it and prove equivalences of theorems. So, okay. So if this guy here is the equivalent of ZFC, then we're going to want to remove axioms from it, right? In the same way that from ZFC, we've removed the axiom of choice. So how to remove axioms from Z2? And the main tool that we have to do that is to restrict comprehension and induction. So here I said that for any formula, we can make the set of elements having that formula, and for any formula, I can do induction. And at the very least, for comprehension, it's like, philosophically speaking, you can see why someone would want to restrict what kind of formulas we have, right? I mean, this kind of thing is exactly what caused cripes, what's the name? Russell's paradox to begin with. So, but how are we going to restrict it? So now I'm going to introduce an idea that for some of you may be already old news, for some of you may be completely new, but I'm going to try to introduce it in a way that hopefully is new for most people. So let's say that you're a mathematician and I write something like this, and I give you a specific formula. I mean, maybe I write x equal to the set of natural numbers such that for every set that satisfies some property, then x is in y. So this is sort of like the intersection of all the sets of y that satisfy this property. This is just an example of something you can do with unlimited comprehension. But if you think about it, this is like a very complicated thing. And if I ask you to tell me like if some number is here, this is going to be very complicated because to check whether, say, 5 is in x, you'll need to look at every set y, which is a subset of the natural numbers. And that's a lot. That's 2 to the aleph naught sets. So you'd have to be doing this job here for more than countably many things before you could confidently tell me that 5 is in fact in x. And so this could perhaps be some sort of like philosophical motivation to say that quantifiers over sets are kind of difficult and maybe we should get rid of them. And so we define an arithmetic formula as a formula without set quantifiers. And the hope is that if you have an arithmetic formula phi, it would be easier to check, for example, if 5 satisfies this formula, because instead of uncountably many things to verify, you'd have at most countably many things to verify. So this is an example of how restricting comprehension work. And this leads us to a system which is called R-C-A-Nought. This A here stands for arithmetic, and the C stands for comprehension. I think this A stands for arithmetic again. And here are the axioms of R-C-A-Nought. So the arithmetic axioms are the same. No matter what systems I give you, I'm always going to say that things like n+1 is never 0. Those are always true. There's no way that those aren't true. But now comprehension, instead of allowing this for every formula, I say for any arithmetic formula phi, I add this axiom. And I will also say that induction is also arithmetic. So for arithmetic formulas phi, I also add induction. And so you can see that this is a weaker system than the one I had before, because now I can't just make every set that I want. Any questions so far? I'm going to wait 10 seconds. Okay. So this is an interesting system. You can see it, well, this is perhaps too simplistic, but you can see it as sort of like if you have ZFC and inside it you have ZF. This is sort of like you have Z2 and inside you have R-C-A-Nought. So it's a weaker system. There are some complicated theorems that you require the extra force to prove, but they're not very common. So, this is sort of like the ZF of ZFC. But the cool thing is that we're going to be able to go even further down, which is something that we can't do with ZF. And so I'm going to introduce our final system, which is called R-C-A-Nought. So let's go back to this idea that quantifiers are complicated, right? I said quantifiers over sets are very complicated, so we don't want them. Maybe now I could say quantifiers in general are complicated. I don't want them, but that would be going a little bit too much. That would get us into trash territory, because you need quantifiers to say basically anything. And there are some types of quantifiers that there's no reason to avoid. For example, if I want to say the sentence that x divides y, divide isn't a symbol in my language, so I actually have to write this as there exists a case such that xk equals y. But this is actually a sort of like harmless use of a quantifier, because it's not like I'm going to have to look for every a, because we know a posteriori that we only need to look at k up to x. So we could actually also write this. And so the point that I want to make now is the following. Quantifiers over numbers are also kind of bad, but not all of them. In the sense that, there are some of them, like the one in the divides, that we really don't want to get rid of this. And so fortunately for us, logicians have already figured out this, how bad quantifiers can be a while ago. and there's this thing called the arithmetic hierarchy. And I don't know how many of you know this. Maybe you all know this, but I was told not to assume that everyone knows this. So I'm just going to give some brief words on this, which is the following. All you need to know about this is that there are two types of formulas I'm going to discuss. So there are formulas called delta 0, 1, which are very nice because a computer can check if they're true or false. So if you have a formula like this, then you can write an algorithm that, given a number, will tell you if that's true or false. That's not true for every formula. And there are also sigma 0, 1 formulas, which are a little bit weaker because a computer can check that they're true, but if they're false, maybe the computer is going to be in an infinite loop and you never know that it's false. But anyway, the point is that logicians have figured out these types of formulas, which are actually defined in a very syntactic way, that sort of have this philosophical appeal because, you know, if there's an algorithm that can tell me whether the formula is true or false for a given number, I like that formula. And maybe I like a set that's made out of that formula. And maybe if I write a set X with a formula that a computer can't check, I mean, does this set really exist if I can't tell if 5 is in the set? So that leads me to our final system, which is called R-C-A-Nought. So R stands for recursive, which is just a fancy word for computable. And so the axioms of R-C-A-Nought, let me put that piece of paper. I lost my axioms. Oh, here they are. Axioms of R-C-A-Nought. So we still have the arithmetic axioms. Those aren't going away. N plus 1 is never going to be equal to 0. Comprehension. What kind of sets can I make? I can only make sets where the formula is a computable function. So I can only make computable sets, essentially. So for phi in delta 0, 1, I allow myself to make the set of elements to satisfy that. And for induction, I'm going to restrict myself to sigma 0, 1 formulas. When I was starting out, I was pretty confused why here we require delta 0, 1, but here we only require this. Like, you know, if this is supposed to be computable mathematics, why are, you know, because these are weaker. And I have some words on this if you want to ask me about it later. But for now, just take it as given that this represents computable mathematics in some way. And so this is our system, R-C-A-Nought, that's going to be the basis for everything we're going to do. Any questions? 10 seconds for questions. Okay. So now, what are we going to do with R-C-A-Nought? We are going to want to prove that theorems are equivalent. And what do I mean by theorems? So I'm going to write some theorems of normal mathematics here. And we're going to see what R-C-A-Nought thinks of them. So theorem, I'm going to call this theorem B for Bolzano. If f is a continuous function from 0, 1 to r, and f of 0 less than 0 less than f of 1, then there exists a real number between 0 and 1 such that f of c equals 0. This is just the mean value theorem. You should all know about it. Another theorem, which I'm going to call W, is that if, sorry, I forgot to say that this is continuous. Another theorem is that if f from 0, 1 to r is continuous, then it is bounded. Another seemingly unrelated theorem is the following. If r, so I'm going to call this theorem P. If R is a non-trivial ring, it admits a prime ideal. And the last theorem, which I'm going to call theorem M, is that if R is a non-trivial ring, it admits a maximal ideal. So I'm sure that hopefully everyone has heard of these theorems. Hopefully everyone will agree that these are definitely like normal mathematical theorems. They're not just something that logicians came up with that no one else cares about. These are like, I mean, we teach these to everyone. And so we are going to find out what R-C-A-Nought thinks of them, but there's one big issue, which is that R-C-A-Nought can literally not talk about them. I mean, because if you remember, in R-C-A-Nought, we only have two types of variables. X stands for a natural number, and big X stands for a set of natural numbers. And there's no type of variable for talking about real functions or for real numbers or for, for any of this, or for rings or for ideals. And so for R-C-A-Nought to talk about these theorems, we need to teach it in the same way that we teach ZFC to talk about these things, right? You know that we can do anything with ZFC because we have all of these complicated ways to represent something as a set. Like a ring is a triple, where the first element is a set, the other is this, the other is that. And in turn, a triple can be defined in terms of pairs, and we have this whole definition where a pair is something like this, right? Because, ZFC does not have a primitive notion of pair, it only has sets, and so we have to teach it. So all of that work needs to be done for R-C-A-Nought. So for example, in R-C-A-Nought, the notion of pair is introduced like this. So when I write a pair of numbers, what I actually mean is this third number that's built out of the two of them. Because if I don't have this, then I can't talk about, for example, sets of pairs, and so I can't talk about functions. And so you can see that there's a lot of work to be done here. A lot of work which I will not do because I have 15 minutes. So this is what I meant when I said that there's a lot of technicalities and they have to be done for you to be able to prove anything. So I'm going to have to sweep them under the rug so I can talk to you about the big picture. And so for now, you should just trust me when I say that we can talk about these objects. We can represent them in terms of natural numbers and sets of natural numbers. And so the first theorem of R-C-A-Nought that I'm going to tell you is the following. The mean value theorem, which is the one that I called B, is trivial, i.e. R-C-A-Nought proves B. So if you ever have calculus students who are struggling with this theorem, you can tell them that they're being stupid and that the theorem they're having trouble proving is actually trivial. And so why is this true? So very, very, very roughly, the idea is that the mean value theorem is computable because we have an algorithm that tells you how to find the C. It's called a bisection algorithm. You've probably heard of it, right? If you have a function that does this and you want to find a zero, what you do is you cut the interval in half. You look at the middle and you say, well, is the function above or below? If it's above, I look at the left half. What now? I cut it in half and I look at this subinterval, and I cut it in half and I look at this subinterval, and this gives me a sequence of numbers that converges to my root of the function. So to prove this, you basically implement the bisection algorithm. You show that this theory can prove that it works, and so the theorem is proven. Any questions? Okay. So Now let's go to another theorem. So if this theorem is really easy, what about this one? If you have a continuous function, then it's bounded. Let's look at a standard proof of this fact and see, if we can expect to do it in R-C-A-Nought. So maximum value theorem. So let's say that you have a function f from 0, 1 to r and that it's continuous. And let's suppose for contradiction that f is unbounded. So for every real number, there exists some x such that f of x is bigger than m. So here's how a normal mathematics proof that this is a contradiction would go. You take the interval and you cut it in half, and you say, well, if the function is unbounded, it must be unbounded on one of the intervals. Let's say it's unbounded on this interval. If the function is unbounded here, I cut it in half, it must be unbounded on one of these subintervals. And you go to that one, and you keep cutting it, and you get the sequence of intervals that's getting smaller and smaller, and the function is unbounded on every one. And you can prove by Cauchy things that there's some real number in all these intervals. And so f of c takes some value. Let's say that f of c is this guy, but then by continuity, you could get this boundedness near c, which contradicts like the tiny intervals around it where the function is unbounded. I mean, this is a very sketchy proof of this theorem in normal mathematics. And now one thing that we usually do in reverse mathematics is we'll open up a calculus book, we'll look at how the usual proof is, and we ask, can we do it in R-C-A-Nought? And the answer here, surprisingly, turns out to be no. At first, these look like very similar algorithms. In both cases, you are splitting it in half, and you are choosing one half, and then you're keeping that going, and you're getting a decreasing sequence of intervals. But the difference is, in this case, a computer can figure out which interval it should go to, because all you have to do is you have to evaluate the function at the point, and you have to check if it's positive or negative. Here, if I tell you that I have a function which is bounded on one of these two intervals, or which is unbounded on one of these two intervals, how are you going to figure out which one? There's no way. You'd have to look at every point. So this is the reason why R-C-A-Nought does not prove the maximum values here. Now, before getting into these two theorems, especially given that I only have 5 or 10 minutes, I am going to very quickly rush through a very important idea, which is the idea that organizes everything, which is the following. The essence of this theorem, which R-C-A-Nought does not have, is that, okay, so I have this whole process where I have these decision trees, right? I should try to figure out whether I should go to the left or whether I should go to the right. And the thing is that I can't really tell which side I should go to, but I know that in the limit there's a path. That in the limit there's going to be a way for me to keep going where I always go to an unbounded interval. And so the thing is that I don't know in principle which one to go to at any given time. And so logicians figured out a way to distill this into the following theorem. Actually, I'm going to write it here in the list of theorems. It's called WKL, which stands for weak Koenig's lemma, which is that if T is an infinite binary tree, it has an infinite path. And so I'm not going to be able to prove this, but R-C-A-Nought does prove that if you have this theorem, then you can prove the maximum value theorem. This is surprising. I mean, these are two theorems that look like they have nothing to do with each other. One of them talks about continuous functions, the other talks about infinite binary trees. And yet, one of them implies the other. And more surprising yet is that this is an equivalence. So if you have this thing, this theorem about real functions, and you are given an infinite binary tree, you can use it to figure out an infinite path for the tree. And so this is really the essence of reverse mathematics. Now, so let's look at these other theorems for a little bit. Let's look at a theorem that any non-trivial ring admits a prime ideal. In normal mathematics, we just prove the stronger one, that it has a maximal ideal, right? We go to the thing and we apply Zorn's lemma to this collection, and that gives us a maximal ideal. So that proves this theorem. And every maximal ideal is prime, so that also proves this theorem. So, I mean, R-C-A-Nought proves trivially that M implies P. Now, if you try to prove M directly, you're going to have a lot of trouble. I will get to that in a moment, but let me look at P for a moment. How would you prove theorem P? So remember that R-C-A-Nought is all about algorithms, so we have to figure out, we have a ring, and we have to figure out how to construct a prime ideal here. And let me just give you some idea of how that might go. You want to build an ideal. Well, every ideal must have zero. So you get a bag and you put zero in it. And now the question is this a prime ideal? And in a lot of rings it is. I mean, there's a whole name for rings where zero is a prime ideal. They're called integral domains. So maybe you got lucky and this is already a prime ideal. But maybe it's not. And if it's not, then that means that there are two elements, A and B, such that A, B are in your ideal. In this case, there's zero. The product is zero. And so you have to add one of them. But which one? You don't know a priori which one you should add, because remember, you're also trying to avoid the ideal from becoming the whole thing. So for example, this guy happens to be invertible. If you add it, you just get the whole thing and you get the triviality. So you have to add B instead. But you don't know that. You don't know which one to add. So add A or B, but don't know which one. And maybe you can see where this is going, because now what you're going to do is you're going to make a decision tree. You're going to say to add zero, then you find some pairs whose product is zero and you add one of them, but you don't know which one. In this case, maybe you find some other pair, A prime, B prime, whose product is in this ideal, and then you have to add one of them, but you don't know which one, and so on. And so you make this binary tree of decisions. And if at any point you run into one, you say, oh, there's no way I'm going to add one to my ideal because I don't want it to be the whole thing. And so you get this binary tree. And now you can somehow prove that this tree is an infinite tree. And so if you can find an infinite path through the tree, then that means that you've never actually added one. And so that this thing is going to be a prime ideal, roughly speaking. Again, I'm not trying to pretend like I'm proving anything, but I just want to give you the idea that R-C-A-Nought proves that WKL implies that the existence of prime ideals. There's some clever way in which you can do it. And again, surprisingly, the reverse is also true. If you know that for any ring there's a prime ideal, then given a binary tree, you can make a ring in a very weird and specific way, such that if you can find a prime ideal for that, you can recover a path for the original tree. And finally, so what have we got so far? We have that this theorem is trivial. This theorem is equivalent to this theorem, which is equivalent to this theorem. And finally, just to say something about this one is actually strictly harder. So this one implies, but is not implied by these three other theorems. And as it turns out, under R-C-A-Nought, the existence of maximal ideals is actually equivalent to A-C-A-Nought. And if you don't remember what that is, let me get my piece of paper. A-C-A-Nought is this like system that we've already discussed before that's much stronger than R-C-A-Nought, that allows for any kind of quantifiers over numbers. So somehow this theorem is really, really, really powerful. Okay, so I'm running out of time, so just a few more words that I want to say about the big picture of it all. So, because I gave you sort of a microcosm, I gave you a few theorems, but what does this look like? You know, if I do this for a long time, what does the picture look like? So we have here at the top Z2, the strongest system. At the bottom, we have R-C-A-Nought, the weakest system. This is not actually true. There are some crazy people who go below that, but I'm not one of those crazy people. We have A-C-A-Nought here, which is a system sort of in between. We've seen that R-C-A-Nought plus the weak Koenig's lemma, which I'm just going to refer to as WKL-Nought. This is also equivalent to some other theorems. And there's also a couple of theorems up here which I haven't talked about, which are ATR-Nought and pi11CA-Nought. And these 5 sets of axioms, which are linearly ordered, are called the Big Five. And the reason they're called that is that if you go to a mathematics book, mostly undergrad mathematics book, maybe graduate textbooks if you're not going into combinatorics or logic, you will find that under R-C-A-Nought, any theorem that you find is going to fall into one of these 5 categories. In the sense that under R-C-A-Nought is either trivial, or maybe it's equivalent to WKL-Nought, or it's equivalent to the maximal ideals, or it's equivalent to some other things that are stronger. And this is really surprising because, I mean, you have this whole body of mathematics, and I'm telling you that any theorem almost can be organized into one of these 5 little boxes. And just to finish the talk, I'm just going to give you a quick curveball, which is combinatorics, especially infinite combinatorics, is one of the few areas that dodges these boxes. So for example, you might have heard of Ramsey's theorem. I'm talking specifically about the infinite version. So that if you have an infinite graph, then you can find an infinite number of vertices which are all connected or disconnected. As it turns out, that is strictly stronger than R-C-A-Nought, but strictly weaker than A-C-A-Nought, and it is not comparable to WKL-Nought. So we have this sort of like weird diamond shape. But this is one of just a few isolated examples. And looking into those examples is something that is currently being done in active research. Okay, I'm done.